In this section, we want to look at the number one rule of solubility, and that is that like dissolves like. I think we mentioned a little bit about solubility way back in chapter 4 when we were talking about solutions, molarity, electrolytes. So this kind of comes back a little bit now here too. Like dissolves like, meaning that polar solvents dissolve polar solutes, and nonpolar solvents dissolve nonpolar solutes. So it comes back a little bit again here when we're talking about polarity and intermolecular forces. Like dissolves like. Now, when I think about it, when I go back to chapter 4 earlier in the year, we said, yeah, something like water is very polar. So water molecules have lots of regions of charge. There's a bunch of water molecules. The oxygen end is partially negative, and the hydrogens are partially positive. And so if I've got a beaker full of water molecules, they all kind of purposely align so that opposites attract, right? So maybe here I've got another water molecule. All the little hydrogens are attracted to the oxygens on neighboring molecules. Like dissolves like. Okay, so anything else that's got a charge is attracted to water molecules. So it could be other molecules that are polar, that have these partial positive and partial negative regions. They would align themselves so that they're attracted to the partial positive and partial negative regions of the water molecule. It could be ionics. Ionics have strongly charged ions that are very attracted then to the opposite regions of a water molecule. So in order to dissolve in water, you got to have a charge. There's got to be some kind of attraction between this new solute and the charged polar water molecules. Now what happens if I add something that's nonpolar? Well, the water molecules then are more attracted to themselves. There is attraction amongst these water molecules. They're all charged, right? So this hydrogen is attracted to this oxygen, and here's attraction. These guys are attracted to each other. Now, if I add something else that is also polar, that's also got a charge, then the water molecules are like, yeah, come on in here. We'll show attraction to you as long as you have a charge. But if I add something that has no charge, like a non-polar molecule, then these water molecules are very disinterested. And in fact, they kind of say, well, you know what? We're just going to hang out together. We're going to stick together because we've got attraction amongst each other. And if I add something that's nonpolar, it doesn't show any attraction for the water molecules. So they become more attracted to each other than they are for these nonpolar molecules. And then there just is no mixing. If the water molecules are more attracted to themselves, and they don't allow in these nonpolar molecules, there's no mixing, there's no solution formed. So like dissolves like. In order to dissolve in water, you've got to have another charge. If I'm going to mix something, if I want to dissolve something that's nonpolar, then it also needs to be a nonpolar solvent so that nothing has a charge, so that all of the particles then are willing to mix with each other. Whereas here the water molecules are going to be more attracted to themselves than they are to something that's nonpolar. Now let's say I find some particles that are the same polarity, like dissolves like. Now there are kind of 3 steps to forming a solution. Step number 1 and 2 are kind of similar. In step 1, we have to separate the solute into its individual components, often referred to as expanding the solute. Often, this is an endothermic process. We've got to add energy to separate these red solute particles. Now, if that's an ionic solid, we got to add energy to separate those charged ions. Even if it's something that's polar, we're going to have to add energy to separate the polar molecules. Now, if it's something that's nonpolar, we probably just don't have to add a lot of energy because there's no strong attractive forces, just those weak London dispersion forces if it's a nonpolar solute. But I am going to have to add a little energy to expand or separate the solute. That's the substance that we're trying to dissolve. So this ends up being, I'm going to put a little positive in there. It's a positive delta H. It's endothermic. Now I also have to do the same thing to the solvent. So it might be water molecules. We want to overcome some of those intermolecular forces between the water molecules to make room for these new solvents, whether it's ions from an ionic solid or whether it's polar molecules. We refer to this as expanding the solvent. We want to separate the solvent a little bit to make room for these new solute particles. This is also endothermic. I'm going to put in a little positive down here. It's an endothermic process to expand the solvent and the solute. Both of those endothermic. So now I've got my expanded solute and solvent, and I'm ready to mix them together. So now if these particles want to interact with one another, energy is usually released. So if I've got oppositely charged particles, I've got two polar substances, when opposites attract, that's a favorable process, and energy is released. This is often exothermic. Again, as long as there is a favorable interaction between the solvent and solute particles, meaning that like mixes with like. So if there's charges, then those charges are going to be attracted to each other, and as they mix them, this becomes an exothermic, a negative process. Favorable. Now, the overall energy change is called the heat of solution, or delta H SOLN, heat of solution. And it really is just the sum of these three processes. Now, often the first two, again, are endothermic, and the third process is exothermic. Now, sometimes I dissolve a substance in water and it is noticeably exothermic. Well, then it must be step 3 that's dominant. Even though I had to add a little bit of energy to expand the solvent and solute, I must be getting so much more energy back when those particles interact with each other that if step 3 dominates, then this exothermic process could become larger than those two endothermic processes, and overall energy is released. It reminds me a lot of that whole bonds broken minus bonds formed thing, that the overall energy change is the sum of two processes. Here it's kind of like 3, although steps 1 and 2 are kind of similar. I've got to add energy to separate the particles of the solvent and the solute, but I get energy released when the particles mix, as long as it's a favorable interaction, meaning that they're both polar or they're both nonpolar. Now, sometimes you dissolve something in water and it's noticeably cold. It could be endothermic. And then that would mean that steps 1 and 2 are dominant. I have to add more energy to separate the solvent and the solute compared to the amount of energy I get back when they interact. Even though I'm still getting energy released when they interact, steps 1 and 2 were just more dominant. It took more energy to separate or expand the solvent and solute compared to the amount of energy that's formed when the solution mixes. So delta H SOLN, heat of solution, could be endothermic or exothermic. It kind of just depends on these processes. And it's kind of a combination of this one versus this one. 1 and 2 being endothermic, step 3 releasing energy. Again, as long as it's like dissolving with like, that it's a favorable interaction. And that's really all we need to know about solution formation for now. So here there's this table about different types of energy formations, and we don't need to worry about that. We just qualitatively can look at this as a kind of like a 2.5 step process. 1 and 2 kind of go together versus step 3. Which one is dominant? Well, that'll determine if the overall energy change for the solution formation is exothermic or endothermic.